Okay, so let's do an example here in which we have a series of things happen. So let's imagine that we've got two power supplies here. We have a resistor here, we have a resistor there, we have another resistor, okay, and then we have a resistor here. So we can call that V1 and V2, or you could call it EMF1 and EMF2. I don't really care which way you call that. And then we call this R1, R2, R3, and R4. Okay, so EMF1, let's say, is going to be equal to 4.7 volts. EMF2, let's say, is going to be 6.5 volts, or 4.70, 6.50. Okay, so R1, let's let R1 be 100 ohms. Let's let R2 be 50 ohms. Let's let R3 be 75 ohms. And let's let R4 be 66 ohms. And so what I want to know is, what's the total power supplied? What's the total power dissipated? How much power supplied by each power supply? How much power is dissipated in each resistor? So remember, for power supplied, that's going to be I times V. Power dissipated is going to be I squared R. So we got to find current, okay? So we look at this and we say, well, what's going to happen is we have current that's flowing here. So that's my total current, but when the current gets to this part, it's going to split. Some of the current's going to go there and some of it's going to go there. I can call that IL and IR for I left and I right. And then we have current here. Now that is the same current as this because there's nowhere for it to go. So what we see is that IL plus IR has to equal the I total right here. Okay. Remember, current in equals current out for a junction. All right, so now we look at that and we say, well, we need to find out how all this works. Well, we've got two power supplies in series, and so they're going to work pretty much like resistors in series. So that means that we imagine replacing this with some total power supply here and some equivalent resistance right there, and use that to find the total current. So all we got to do is find this equivalent resistance, because the total here is going to be E1 plus E2. So how do we find the total resistance? Well, we've got here R1, R2, R3, R4. Well, these two are in series. So R2 and R3 are in series, so that's going to act like 125 ohms. So now we have what looks like this. Have 125 ohms there. R1 is 100 ohms, and this down here is 66 ohms. Well, 100 ohms in parallel with 125 ohms. How do we figure out that? Well, that's going to be 1 over 100 ohms plus 1 over 125 ohms, and all of that to the minus 1. So that's going to be the equivalent resistance for the top part up here. And so what does that come out to be? 55.6 ohms. Now we have 55.6 ohms in series with 66 ohms. So the equivalent resistance is going to be 122 ohms. So now we have the total voltage we have the equivalent resistance, and we want to find the total current. So the current is just going to be V over R. So that would be, well, the total here is going to be 11.2 volts. And we have 122 ohms. So that comes out to be 0.0918 amps, or if you wanted to write that as 91 milliamps, that would be fine too. All right, so either way is the correct way of writing that. So now we go backwards and we say, okay, so we have here in the top, we have this, we have that, we have this, we have the bottom R4. Well, we know the total current is the same current going through R4. So that means the current in R4 is the 91.8 milliamps. That means we can find the voltage on R4. The voltage on R4 will be I4 and V4. Or sorry, I4 times R4. Okay. And so that is going to be equal to 0.0918 amps times the R4, 66 ohms. So V4 is going to be equal to 6.06 volts. Well, what about this up here? What is the V in the top part up here? So the V top would be, well, remember this is an equivalent resistance up here. We have the equivalent resistance up here, so this acts like it is one resistor that is 55.6 ohms. So the V up there is, so the V in the top up here is going to be equal to the 0.0918 amps times 55.6 ohms. So the voltage on the top part comes out to be 5.10 volts. Now, this voltage and that voltage should add up to the total of 11.2. Well, it adds up to 11.16. Well, that rounds to 11.2. So within rounding error, it does add up properly. All right. So if it did not add up properly, we would have done something wrong. We would have known we did something wrong, and we had to go back and fix it. So we checked and made sure that this voltage plus that voltage adds up to the total. So this voltage plus that voltage adds up to the total voltage within rounding error. Okay. Now for R1, we know that the voltage there is 5.1 volts. So I1 is going to be 5.1 volts over 100 ohms. So that's going to be 0.0510 amps, or in other words, 51 milliamps. For the other side there, where we had R2 and R3, now remember that makes an equivalent 125 ohms, okay? Then that means that the current through there, so the current on the right there is going to be 5.1 volts over 125 ohms. So that comes out to be 0.0408 amps, or in other words, 40.8 milliamps. Okay, so what's the voltage there? What's the V2 and what's the V3? V2 equals the I times R2. V3 equals the I times R3. So if you multiply that out, what you get is 2.04 volts and 3.06 volts. Now, if we did it right, remember this is in parallel with that R1. That was a total of 5.1 volts. These should add up to 5.1 volts. They do. So that means that we have a good chance of having done this right. Furthermore, we know that we had current here, And we knew that this was down at the bottom 91.8 milliamps. We found that the current in the top left up here was 51.0 milliamps. The current in the right over here was 40.8 milliamps. Now you have the same current going through both R2 and R3 because they're in series. Now, if we did it right, these two currents at the top should add up to the current at the bottom because current in has to equal the current out. We look at it, it does. So that means we probably did that right. Okay, so now we want to see, we've got the voltages and we got the currents for all the resistors. Okay, we've now got the voltages here for the power supplies. They're given, so I want to know, okay, so we know the total current through there is 91.8 milliamps, or in other words, 0.0918 amps. So this is the EMF 1, that's the EMF 2. So I want to know what's the power supplied. Power supplied is I times V. So that means for P1, it's going to be 0.0918 amps times 4.7 volts. So that turns out to be equal to 0.431 watts. For the other one, that's going to be power 2 is going to be 0.0918 amps times the 6.5 volts. And so that will come out to be 0.597 watts. What about current dissipated? The power dissipated rather. That's going to be I squared R. So if you work that out for R1, R2, R3, and R4, we have the R values given. The I's we already calculated. So if you work that out, I squared R for each one of those. So that means that power dissipated in 1 is going to be 0.26 watts. Power dissipated in 2 is going to be 0.083 watts. Power dissipated in 3 is going to be 0.125 watts. And power dissipated in 4 is going to be 0.556 watts. So the total power dissipated comes out to be 1.024 watts. Power supplied, that was the IV. The total power supplied was 1.028 watts. If we did it right, these two are the same. And they are correct within rounding error. And so that means we probably did this correctly, or at least we have a chance of doing it correctly. And in fact, it's a very good chance, because look at all the math that we did. We did an awful lot of math in here. And the chances of doing all that math and making mistakes and still accidentally getting the right answer is highly unlikely. So with this, we could say that we probably did this right.